Hello friends, welcome to Learner's Planet. Friends, this is our second session for real numbers. In the previous session, we discussed about different types of numbers. Then we discussed about Euclid's divisor lemma. We discussed some problems based on HCF. Now in this session, we'll be taking some more problems to find out the HCF of two numbers by Euclid's method. And then we'll discuss some more theorems on real numbers. So let's begin the session. Now, use division algorithm to find HCF of 336 and 54. That means we have to use the Euclid's method to find out the HCF of these two numbers. Now, what's the first step? Divide the bigger number by the smaller number till we get 0 as remainder, right? So, 336, we divide it by 54. So, it will be 6 times 54 into 6. So 54 into 6, we got 324. So 12 as remainder. That means the remainder is not 0. That means the HCF of 54 and 336 is not 54. Now what is the second step that we had discussed in the previous lecture? Now we divide 54 by this number. That is the remainder, right? Now what is 12 fours are 48. And this is 6, right? So still the remainder is not 0. That means HCF is not even 12. Now we put 12 over here and we divide this by this remainder, that is 6. So 6 2s are 12. Now the remainder is 0. So when the remainder is 0, at that time, what was the divisor? It's 6. So 6 is HCF of 6 and 12. So 6 is HCF of 12 and 54, and hence 6 is HCF of 54 and 36. So HCF of 336 and 54 is 6, right? I hope you are clear. Now let's see this question. We have to find out the HCF of 960 and 432. Now how do we do that? The bigger number to be divided by the smaller number. So 432 here and 960. Now 432 2 times are 864. So we are left with 96. Now the remainder is not 0. That means HCF of 432 and 960 is not 432. Now next step, we divide this divisor from this remainder, right? So 432 we divide by 96. Now 96 4 times is 384, right? So it's 12 minus 4 8, and it's 13 minus 9, it's 48. So still the remainder is not 0. That means we have to go for further one more step. So now I take 96 as dividend. Now 48 2s are 96. Now we get the remainder as 0. That means this number, that is 48, is HCF of 960 and 432, right? Because in this step we are getting 0. So HCF is 48. Okay. Now friends, let's discuss the theorem, that is fundamental theorem of arithmetic. What it says: every composite number can be expressed, or every composite number can be in fact factorized as a product of primes, and this factorization is unique apart from the order in which prime factors occur, right? That means precisely we can say every composite number can be expressed as a product of primes. Suppose I have an example, maybe number 6, right? Now we can express number 6 as 2 into 3, right? Where 2 is a prime number and 3 is a prime number, right? So likewise we take more examples. Suppose 48. So 48 is equal to 2 into 2 into 2 into 3 and one more 2, right? So 2 2s are 4, 2s are 8, 2s are 16 into 3, 48. So 48 can be expressed as this, right? So it's 2 is to 4 into 3. So similarly, we can factorize the other composite numbers also. So that will be more numbers or more practice we'll be doing in our problem solving session. As of now, let's proceed with the next concept. So let's discuss application of fundamental theorem of arithmetic. Now it's related to multiplication of positive integers. It is known that composite numbers can be expressed as a product of primes in a unique way. This important fact is the fundamental theorem of arithmetic, right? Now we use the fundamental theorem of arithmetic for two main applications. First of all, to find out the HCF and LCM of positive integers. Then to prove the irrationality of many of the numbers such as root 2, root 3, root 5, something like that. More and more examples are there, right? Then the third is to determine the nature of the decimal expansion of irrational numbers, right? Now we apply this theorem to explore when exactly the decimal expansion of a rational number, say p by q, see the necessity is there that q should not be equal to 0, is terminating, or whether it is non-terminating repeating, right? Okay, so we do so by looking at the prime factorization of the denominator of p by q, right? That is denominator q, right? So these are the main applications of fundamental theorem of arithmetic which I described over here. So it will be clear to you once we will be doing the problems, right? Now friends, let's discuss the algorithm to find out the HCF and LCM of two or more positive integers, right? So what's the working rule? See, factorize each of the given positive integers and express them as a product of powers of primes in ascending order of magnitude of primes, right? So now what's the meaning of this? Suppose I have a number maybe 48, right? Now 48 is what? 2 into 2 into 2 into 2 into 3. So how do I have to express as 2 raised to 4 into 3? So what is the first step? To factorize each of the positive integer and express them as a product of powers of prime in ascending order of magnitudes of primes, right? So this is how we have to represent each and every number, right? Then to find the HCF, identify common prime factors and find the smallest exponent of these common factors. Now raise these common factors to their smallest exponents and multiply them to get HCF. See the language, if you go linguistically, it will be really difficult for you to understand. But these are the algorithms and which are mentioned in your NCERT books. I'm just referring them. Otherwise, it will be cleared in your mind once we are going to solve the problems, right? So to find the LCM, list all prime factors occurring in the prime factorization of the given positive integers. For each of these factors, find the greatest exponents and raise prime factors to the greatest exponent and multiply them to get LCM, right? So see, in examination, you are not going to, you are not asked about the working rules or algorithms to find HCF and LCM of positive integers, right? You will be asked the questions only, right? So instead of mugging up all these steps, we take some 2-3 problems. So the concept or the steps to find out the HCF and LCM will be cleared, right? Now I take one example where we find HCF and LCM of two given numbers. Suppose I have an example of say 42 and 63, right? So we are going to find out the HCF and LCM by prime factorization method, the algorithm or the working rule we have just discussed, right? And once again, you don't have to mug up the working rules. You just practice the problems because in examination you'll be asked problems only, not working rules, right? Now first of all, we have to prime factorize the numbers. So 42 is equal to 2 into 3 into 7, right? 6 sevens are 42, right? Then 63 is equal to 63 is 9 into 7, so it is 3 into 3 into 7, or we can say 3 square into 7, right? Now we have this and we have this. So to find out HCF, right, that is highest common factor, right? Take the numbers which are common between these two, right? and take the least power of the numbers, right? Now I just change the color of the pen. Wait a moment. Here we have number 2, but here we do not have, right? Now, so 2 cannot be the part of HCF. Now here we have 3 and here we have 3 square, but we have to take the least exponent. So what is the common between 3 and 3 square? That is number 3, right? So we have to take the least exponent. Here it is 3 raised to 1 and here it is 3 raised to 2. So we'll be taking 3 raised to 1 only. Okay, the next is 7 is there and 7 is there. So we take 7, right? So HCF is 3 into 7, that is 21, right? So what HCF is? Highest common factor. So highest common factor of these two numbers is 21, right? Now the next thing is, suppose we wish to take LCM. Now when we have to find out the LCM, we have to take the greatest exponent of every number, right? I just eliminate this. We have this and this. Now we have to take the greatest exponent of number 2. So it's 2 only. Then we have to take the greatest exponent of number 3. That is 3 raised to 2. So it's 3 raised to 2. Then greatest exponent of 7 is 1 only. So it's 7, right? So 7 into this 3 3s are 9. So 9 7s are 63. 63 into 2 is 126. So LCM of these two numbers is 126 and HCF is 21, right? So you got the method. How did we calculate HCF and LCM? I take one more example. Now let's say the next example is maybe 36 and say 84, right? So we have to find out the HCF of these two and LCM of these two, right? So first of all, let's factorize. 36 is 9 into 4, so it's 2 square into 3 square, right? So this is what the prime factorization of 36. Now 84 is 12 sevens are, that means 2 into 3, 6, 6 into 7 is 42, 42 twos are, so that means 2 square, right? So 4 3s are 12, 12 sevens are 84, right? So now first of all, let's find out HCF. Now for HCF, we have to take the least exponent of the common numbers. Now 2 square, 2 we have here and 2 we have here, and the least exponent of 2 is square. So it's 2 square. Then 3, here it is 3 and here it is 3 square. So 3 we have to take, but we have to take the least exponent. So that will be 3 raised to 1. Then 7 we have here, but 7 we don't have here. So we will not take any other number now, right? So it's not there. Now 2 square into 3, that is 4 into 3. HCF will be 12, right? Now what will be the LCM? Now for every number, in case of LCM, we have to take the highest exponent of every number, right? So it's 2 square. Then for 3, what is the highest exponent? That is 3 square. Then for 7, what is the highest exponent? That is 7 raised to 1. So it's 7 only, right? So it's 3 3s are 9. 9 into 4, 36 into 7. So 7 6 are 42, 7 3s are 21 and 4 25. So LCM of these two numbers is 252 and HCF is 12, right? So I hope you are clear with the concept of HCF and LCM by prime factorization method. Now the important thing over here is one more observation is there, that is HCF and, just wait a moment, HCF into LCM of two numbers is equal to product of the numbers, right? So here what is HCF? That is 12, and what is LCM? It's 252, and whatever the number we are getting after multiplying 12 and 252, it will be the same as 36 into 84, right? So this is the important formula that you have to learn, that HCF and LCM of, we are talking about two numbers only. right? So HCF into LCM of two numbers is equal to product of the numbers. So that's actually an important formula, or we can say an important relationship, right? Friends, we will be doing more problems on this. First of all, as of now, let's take more concepts, and we'll be doing more problems in problem solving sessions, right? Now the next thing is we use the basic or the fundamental theorem of arithmetic to prove the irrationality of many of the numbers. Now we have already discussed in our previous session what are irrational numbers, and you must be aware of that. So to prove the irrationality of many numbers, we use the fundamental theorem of arithmetic, right? Now just have a quick recap. What is an irrational number? The number which cannot be expressed in decimal form either in terminating or in repeating decimals are known as irrational numbers, right? That means an irrational number cannot be written in the form of p by q, where p and q both are integers and the denominator is not 0, right? Further, we see the algorithm how to prove the numbers are irrational. And once again, I'm telling over here that it's just algorithm. You don't have to mark up. The ultimate method we will be discussing while we'll be solving the problems, right? So what's the theorem over here? We use the method of contradiction to prove the irrationality of numbers, right? Now what's the theorem? Let p is a prime number if p divides a square, then p divides a, where a is a positive integer. Now let's discuss the proof, and this proof will not be asked in the examination. It is just the given in the NCERT textbook, so I'm discussing it over here. So here, see, we take any number, maybe a, right? And a number can be factorized, and the factors of a are p1, p2 till pn, right? Where p1, p2, every number is a prime number, right? Okay, and not necessary to be distinct, right? Now what's a square? A square will be square of all these numbers, that is p1, p2 into till pn and into p1, p2 till pn. So that is precisely p1 square into p2 square till n square, pn square, right? Okay, that is pn square into p2 square into pn till pn square, right? So that's what is a square. Further, I would repeat, a is any number, and that is the product of these primes is actually a, and where it is not necessary that p1 and p2 and pn are distinct. Suppose I have number 48, so 48 is actually 2 raised to 4 into 3, right? So 2 is one prime number and 3 is other prime number. So I can write down 48 as 2 raised to 4 into 3, right? Now we are given that p divides a square. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square, right? So, however, using the uniqueness part of fundamental theorem of arithmetic, we realize that only prime factors of a square are p1, p2 till pn. So, p is one of p1, p2 and pn. So, a is equal to p1, p2 till pn and p divides a. Now I take the example to elaborate this, as we are discussing about 48. So 48 is 2 raised to 4 into 3. Now suppose this is what a. Now a square will be what? It's 48 square, that is 2 raised to 4 whole square. So we can say it's 2 raised to 4 whole square into 3 square. So that is 2 raised to 8 into 3 square. That's what? 48 square. Now according to this theorem, if any number p, right, if any number p divides a square, right, and this p is actually a prime number, right? So any number p that divides this a square, then according to the fundamental theorem, right, it will be definitely a prime factor of a also, right? Because if it is the prime factor of a square, right, so it will be prime factor of a also, right? So we can see it's over here. See, 2 is a number that is dividing a square, and 2 divides 48 also, right? That is 2 is dividing 48 square, that means 2 will divide 48 also, right? So this is how this theorem is explained, right? Similarly, other numbers may be 3. So 3 is a prime number, that is 48 square is divisible by 3, or we can say 3 is dividing 48 square. That means 3 will definitely divide 48, right? We'll be taking more problems on that. Now next is how to determine the nature of the decimal expansion of rational numbers. Now we know the rational numbers and irrational numbers taken together are known as real numbers, right? That we have already discussed in the previous session. Now we can say that any real number is either rational or an irrational, right? Now the first theorem which is used to determine the decimal expansion of rational numbers, right? Now suppose we have a rational number, that is x, and whose decimal form of terminates, right? Then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q is in the form of 2 raised to n into 5 raised to n, right? Where n and m are non-negative integers, right? So a fraction will be terminating only when its denominator is multiple of 2 or 5, or we can say 2 and 5, right? So just by looking at the number, we can say whether it will be a terminating decimal number or not. Suppose this is 3 by 5, right? So in denominator we have 5, right? So this is a terminating decimal number. That means it is like after 0, after decimal it will terminate, right? Maybe after 1 or 2 numbers, but it will be terminating, right? But suppose we have 3 by 7, right? So we want the 2 or 5 in the denominator. So if we see 7, it will definitely be a non-terminating, right? Suppose we have 3 by maybe 2 raised to 2 into 5. Now we have just 2 and 5 in the denominator. So further we can say it will be a terminating, right? Rational number we can say. Now suppose I have 5 by 19. So it will be non-terminating because we do not have 2 and 5 in the denominator. Friends, to check whether this will be terminating or not terminating, you just look at the denominator. If the denominator consists only 2 and 5s, then it will be a terminating rational number. If denominator contains any number apart from 2 and 5, then it will be non-terminating. Suppose I have maybe 5 by say 90, right? So first of all, what I would do, I just convert into simplify it is 1 by 18, right? Now in denominator I have 9 also. 1 by 18 is what? 1 upon 2 into 9. But we don't want 9, right? So 1 upon 2 by 2 into 9, that is 1 by 18, will be a non-terminating rational number, right? I hope you are clear. So from these explanation we can conclude that the decimal expansion of every rational number is either terminating or non-terminating, repeating, right? So every rational number can be expressed as p by q, where q is not equal to 0. If q is in the form of 2 and 5, then it will be a terminating decimal expansion. If q is not in the form of 2 and 5, if any other number is also there, then it will be non-terminating recurring decimal, right? But in both the cases the numbers will be rational numbers only, right? So I hope you are clear with the concept of rational numbers and the theorems which we discussed, that is basic fundamental theorem of arithmetic, right? Friends, in the next session we'll be taking problems based on all these theorems and concepts. So do revise this session and the previous session, because next session is going to be some interesting fun session, because we'll be taking the problems now, right? Bye bye.